we can also interact with the legend. We can dim all of the brain nodes, or the healthy tissue nodes, and further draw attention to the tumor nodes. We can make the brain nodes, the healthy brain tissue nodes, a little bigger when they're dim state to give context to the tumor nodes without distracting from them or obscuring any of them. So they are at this point translucent. See, if one cube obscures a set of spheres, it still shines. The spheres still shine through. And we have different color codings available here. We can color them by, say, their degree centrality. So in this color scheme, the squares represent the brain nodes, the healthy tissue nodes that are not masked from the tumor, and we can click on them and gray them out. And also reduce their size. Maybe increase the size of the spheres so you can really see the tumor regions in the context of which brain anatomy regions they're belonging to, they're situated at. And you can also see how the different clusters have different how the different values of degree centrality spread across the different clusters. So we can select some high degree centrality regions. See what other tumors and what other clusters they connect to. Looks like they're all pretty much connecting one cluster over here. And we can change the color coding back to clustering and look at the same data again. So we can click on all of the nodes in a given cluster of interest. See, this cluster seems to have a very high centrality. You can see how that cluster is oriented in the tumor's anatomy. So selecting all the nodes in one cluster on the left and comparing that information to in the anatomical view on the right, we can see the network map of how a specific cluster, which kind of represents a cell type, how that permeates the tumor set of the patient. It seems like it has a presence in pretty much all of the tumors there. So that cell type is shown to be kind of ubiquitous among all the tumors in this patient. I don't really see any tumors that don't have any of the cell type in it. And we just picked a high degree centrality cell type. We wanted to try it, the clustering coefficient view. It's not too useful. The average path length. Wanted to take a look at nodes with an average, colored by their average path length. Those are kind of short. Try to light up this whole cluster that contains the two nodes with the one of the shortest path length, average path lengths. That cluster is somewhat prolific, but this cluster, this tumor here, does not have any cells of that cluster in it. So that might be an interesting finding. Perhaps this cluster of cells evolved after this tumor was already established, and they have kind of a founder mutation that this one doesn't have. And switch back to cluster coloring again. We'll select all of these nodes again. So that cluster is very clicky. It has a very high clustering coefficient, it seems. And most of the tumors have members of that cluster in it, have regions of this one. This tumor does not. It contains only these clustered cells. You can highlight them, and you can discover which cluster they are. They're all this cluster. And that's the most ubiquitous cluster. That's the one we highlighted last time. So my guess would be that this cluster's older and it has this as the cells migrated to other tumor sites, they acquired new mutations that proliferated to downstream tumors, but none of those mutations got back here. Or at least the mutation in none of the mutations in this cluster got back to that cluster. So if I was going to take a biopsy, I might want to pick this cluster, because if that had, since that would have some cell, if I was looking for a representative of all of the tumors. However, if I was looking for a variety of maybe genotypes and phenotypes, I would be missing certain genotypes that are in this one if I only looked at that one. So this tool could help diagnose patients and find on a imaging level and help plan biopsies to get a representative of all of the tumors with as little intrusiveness as possible.